Good afternoon, everyone on site and online. My name is Xiaoyu Zhu from a State Key Laboratory of Fire Science in USTC. It's a great honor to invite Dr. Ulises Rojas-Alva from Slovenia National Building and Civil Engineering Institute, ZAG, to visit us. And this afternoon, he will give us a presentation. Before his presentation, let me make a brief introduction of him. Dr. Ulises Rojas-Alva graduated as a PhD from the University of Edinburgh in 2022. He would obtain his Civil Engineering Master of Science and his Architectural Technologist at the Technical University of Denmark and Polytechnic University of Madrid, respectively. To date, he has worked on a range of research topics, including fire safety on spacecraft, flame spread and ignition of solid materials, in-situ burning of spilt crude oil, smoke management in tunnel infrastructures, hydrogen safety, etc. Dr. Rojas-Alva has collaborated with other research institutes and universities like ESA, ZARM, Bremen University, Aarhus University, University of Liverpool, NOFO, International Association of Oil and Gas Producers, the Cold Regions Research and Engineering Laboratory. He is currently an associate researcher at FRISSBE-ZAG, where he is involved in various core research activities, including safety of lithium batteries, material behavior of engineered wood products, spacecraft fire safety. Okay, welcome to give us a presentation, and his topic is the FRISSBE project and the challenges on the fire safety of lithium-ion battery fire in the built environment. Okay, time is yours. Welcome.
Thank you everyone for being here and hearing me, and also for the online audience. Can you hear me from here? Right? It's fine here. So, as Professor Shia, you introduced me, and I come from Slovenia, although I will explain more in detail my background. And then, so one thing I want to, the introduction itself, the presentation, is that I divided in 3 parts, okay? I hope it's not because by the end of 1800, Peru took many immigrants from Guangdong province, from the southern part of China. That's why in Peru we have, I think, around 3 million people that descend from Chinese immigrants who came to, Cantonese, mostly immigrants who came to Peru. And hence, a lot of our cuisine, our food is mixed with Chinese. And that's why I know some things, and that's why I like Chinese food in general. So at the age of 15, I moved from Spain to Madrid because my parents decided to move to a better bachelor. Then I did 1 year exchange in Denmark, this tiny, tiny country here in northern people. I did 1 year exchange, and then I decided to pursue my master degree in Denmark. There is when I started to deal with fire. Then I went to Edinburgh, Scotland, the UK, to do my PhD. And then once I finished my PhD, I went currently in this very small country called Slovenia in the northern part of Italy. And there I'm working there now and living there for now. And I hope I can stay there for a longer time. This is more my trajectory. As you can see, it's many places, many countries. I'm learning my fourth language, and it's a challenge to move from place to place, but that's what it gives me, like, because whenever I go, I see the good of the things and the bad, so I take the good and I learn from the bad part of each place. And also culturally means that I am flexible enough to another culture. Then my professional development itself. So I already mentioned before my education itself. My bachelor degree was in Madrid. It was technical architecture or technical architectural technologies, and there you learn how to basically design buildings for basic managing buildings. Like you have to construct a building and so on. At the same time, the last year I went on exchange to Denmark because we can get double degree. So I actually have 2 degrees for bachelor, one in Spain and one in Denmark. Once I finished that degree, I knew that I had to have further education, and that's why I did my master's degree. After the master's degree, in between then, I had actually, when I was doing my master's degree, I had to work, and I had 2 jobs besides my education. So I had to study and work at the same time. This is one job I had in Denmark at DTU, Technical University of Denmark. I was teaching assistant, but also on top of that, I was actually cleaning houses to support myself. And then I got a position as a research assistant with Grunde Jomas, Professor Grunde Jomas. Since then, I know him actually. And then once I finished this education, I moved to the UK to pursue my PhD education. Okay, there I did more flame spread of in microgravity environments. Then postdoc, half a year in Edinburgh, and now I'm in Slovenia as a senior researcher. So this is more or less my trajectory, how I see it. So with this, what I want to tell you is, like, in my life, opportunities came to me and I took them, because I had the opportunity to go to Denmark and I thought it was going to be a good chance for me to learn more things. And once I was in Denmark, I could pursue more education. And again, once I moved to the UK, I knew by pursuing PhD education, I knew that it will land me into greater opportunities. And right now in my life, I'm here and I know where I want to go. research-wise where I want to work. So, but that's because it has given me all the confidence and the knowledge and experience, expertise to decide what I want to do in the future. That's because I moved places and I experienced myself. I throw myself into experience to a new country, to a new culture, to new challenges, because every problem I face is a challenge for me, but I'm not afraid of the challenge. I want to have the challenge because I want to think hard and long and start to solve it. Okay, that's more or less how I see life. And I always recommend everyone to really, if you can travel, please do travel abroad, go on exchange, try to talk to people, learn a new language, because that will give you opportunities that otherwise you wouldn't have if you stay in one place. Okay? Then now in this country, Slovenia is a very tiny country. Map. This is Western Europe, and Slovenia is a tiny, tiny country here. It's very tiny. It's 2 million people. Haifa is 10 million. So imagine it's a tiny country. It's next to Austria. You can see here the map. It's like a chicken shape. You see Austria, Italy. Venice is here actually. It's very close. Croatia. The funny part with Slovenia is the language is very difficult, but the country is beautiful. And it's one of the safest countries in Europe, actually. It's very safe. It has always ranks as one of the safest. It's a beautiful country. Look, this is what you see. So Shayu, he was here in this Lake Bled. It's a beautiful lake. These are the Alps. And this is the lake with an island inside. They're very famous. This is very green and lush. Very cute. It's a very small town, but it's very cute. Slovenia has the longest caves system in Europe, actually, because these caves starting in Slovenia and end up in Serbia, Montenegro. They're the longest one. This is a valley called. So, and look at the water is turquoise color, and these are the Alps. It's winter. The country is beautiful itself. It's very safe. It's a nice place to visit. Okay, all good. Any questions so far? No. Okay, let's keep going. Now, second part. Now I'm going to talk about the FRISSBE project itself. And this is a project that I got hired because of the funding that this project brought to the institution. So then I will explain more in detail what it means. So this is actually the institution I'm working at, and it's called ZAG. Let me see if I, there, oh no, there. So basically ZAG, it stands for Zagrad Slovenia. In Slovenia means Slovenian National Building and Civil Engineering Institute. Is a public institute where we do different kind of work, and it's a long, quite an old Slovenia, because it's the only one in the region that do a lot of work with civil engineering, with construction, and so on, even fire safety. But this institution I'm actually currently employed at. Then this is a few numbers about the institute. It's a public research institute, which was founded after the Second World War in 1949. It's quite old. It's a leading institute in the field of construction and civil engineering, even in the region. I think we are actually an excellent center, actually all the way down to Greece, Austria, even Italy. Compared to Italy, we're actually quite at a high level. We're independent. We do a lot of research. More 50%, almost 50% of our activities. It means we do research, as you do here at UTC. And then the activities mean that we do either standard testing, like we do certification, or we do other kind of specific studies, applied research. 270 employees. That's a large institute, big numbers. Many people have higher degrees, and a proportion of us have a PhD. Okay, that explains also why we do a lot of fundamental work. We have actually quite a lot of experience working with international partners, having big projects, Horizon project at Europe, and so on. With domestic projects and so on. And our annual turnover is 14.17 million euros. That was the last year. I think from this year, from 2023, is even higher. It's around 16 million euros, I think. This is okay. Then a little bit how we divided ourselves. We have 6 departments. One is building physics, geotechnics, metrology, materials behavior, the structural behavior, and then the fire-safe sustainable building department, FRISSBE department. So this department before used to be only one unit, one small unit within one other department. But their fire lab they had was from the 60s, was very old. Therefore, ZAG, the institute, funding to improve facilities. So therefore, they applied to this funding scheme. It's called Horizon Widespread Scheme, where the European level you can get funding. We got 5 million euros to bring excellence. And with this funding, we could actually have a new laboratory, a new facility. And you will see the picture later on. But this kind of big project is very ambitious. And then you have to select a good ERA chair. ERA chair means that they select a excellent CV, Professor Gundre Yomas, that he will lead this kind of project where he will create a new ecosystem in the region, doing research and applied research. That's why it says here the ERA chair actions will support universities or research organizations objective of attracting and maintaining high quality human resources on the direction of an outstanding researcher and research manager, the ERA chair holder. This is the meaning of ERA chair holder, and in this case is Professor Grunde Yomas. And change will bring changes to the institution itself. That's why they apply for this project, to lift what the ZAG as an institution had already. So right now we are even more famous. The FRISSBE department is even more famous than the institution itself. And then that's why we're so successful. And we brought quite a lot of funding. Last year, we brought 1 million euros of funding itself. And this funding gave money to hire me, to hire my colleagues, and to have built a new lab. So a little bit about the project. We started in 2021. I got hired here, 2022. Professor Grunde Yomas got hired 2021. More people we hired, and we're still hiring more people. We'll finish 2026. But we are so successful that we already have permanent contracts because we brought so much money funding already. So that's why we're looking for more people. So the different work packages, you can see here the structure. I can explain more in detail later on, but this is the structure we are working on. And we have a lot of deliverables. I mean, I had to submit paperwork for you about this project. Then when we created the department, meant that this fire laboratory and fire engineering unit used to be in this department. Then we merged with that unit. My unit for section for fire research and innovation. We do mainly research, and we created this department, the FRISSBE department. That's more the story of the FRISSBE funding and then the FRISSBE department. Okay, but you can see this is the organigram of ZAG. Different directives is here, all the departments we have in place, and each unit within each department. For instance, you can see in materials, they have a lab for stone, recycled materials, for concrete. In FRISSBE department, at FRISSBE department, we have the fire laboratory and fire engineering, and we got the section for fire research and innovation. Okay. This is the current FRISSBE project team, meaning this is the people who got hired by this funding for this section. Unit for fire research and innovation. So this is Grunde Yomas. Professor Grunde Yomas is here. You can see him. He's the leader of the project, and is also the head of the department. And my colleagues, Martin, Leticia, Ales, Honai, Andrea, Grunde Mieder, Kirils, and Nick, this tall guy. But the department, both units, where you can see a more fuller all the units, because we also have people who do all the technical stuff, all the laboratory work. Now, this is Friedrich Ness, and he is actually the leader of the lab laboratory. We also have interns come to work for us over summertime. Because I was absent for that picture. Professor Grunde Yomas is here. This is a new lab. So with the funding we got for the FRISSBE project, we have new cutting edge lab. I think we are one of the largest labs in the region, actually. When we are one of the few in Europe, we have a 10 megawatt oxygen calorimetry unit. It's quite large lab, and that's why we're quite unique. We get a lot of clients and partners because of these abilities we have in the lab. You can see here a little bit. This is a huge furnace. This is 4 meters by 4 meters. This is another longer furnace. This is for fire resistant testing. I believe you have seen there here. This is an SBI. This is a flame spread apparatus. This is fire under the big hood. This hood. This is 10 meters tall. And this, you saw it. I'm close to show you. And this 10 megawatt fire. You can go here. This is a big lab. So in terms of what do we do in the lab itself or in the department, so divided into these kind of categories. We do materials behavior, numerical methods, experimental methods, emissions of toxicity, and structural behavior. Okay, similar. I mean, some of the things that I'm mentioning, I think USTC also does, but you do have, of course. For instance, one of the topics I myself work a lot is on spacecraft fire safety, or otherwise I look at fundamentally flame spread, laminar flame spread in microgravity experiments. And I'm telling before Professor showed you that next year I will be doing experiments, flame spread experiments in lunar gravity. So I go to Germany and to drop tower, where I actually, for 5 seconds, I have 9 seconds, sorry, where during 9 seconds I see how the flame behaves, and I look at the heat transfer, I look at the extinction phenomena, and so on. And you see, we also have other projects that these are not mine, but bio-based coatings, low vibration track ballast, protein-based timber ID, electric storage, lithium-ion batteries. That's something I also work on. Wood modification, we also have a project where wood is modified, and we look at the fire behavior. Then we have also thermal mechanical behavior of wood, PV panels too, something you also do, I think. Facades also we do. Hybrid testing. Then we have massive timber structure, like structural behavior, and some other things like on fire safety sustainability. We look at toxicity with these two, FTIR and GCMS. So these are all the activities we do in general. And I'm particularly, myself, I involve spacecraft. I look at lithium-ion batteries, wood modification, and facade fires, and then fire. These are the projects I'm currently involved in. There are a bit too many, but we are very busy because we got quite a lot of funding actually. So next is, so as you can see, we have a lot of projects. We're very good at bringing funding, but also we're good at, therefore I'm here actually to reach out to you personally, because we collaborate with many people around the world. You can see many people visit us. We give presentations, we organize conferences, workshops, and so on. We organize ourselves, also when we have people around. We always strive to reach potential partners to collaborate with, because I think when you combine the efforts of many people that are good at something, you can achieve greater outcomes, right? And this is actually a map of all the countries we actually have collaborated with. We have kind of at a personal level, and at the group level. These are all the countries we have actually, and I include China here, Australia, even some of my colleagues, Spain, the UK, Scandinavia. So we reach out kind of the world more or less. As you can see. And one particular collaboration we have in place, and also it's the same for you, for USTC, is that we collaborate for the International Master of Science and Fire Safety Engineering. You know, this IMFSC program is a very specific one in Europe, one unique of a kind. And that's also that's why we get interns, students coming from this program to work with us for a summer or the final project with us. And you can see a picture. These are our interns that they came from. This guy, he's from France. Then the rest are the MFSC students, and then this guy also from France. That's why we always say there are many ways. Either you come for a research visit, you can also have you as an intern working with us, or yes, there are many ways. So we are actually next year hosting the next European Symposium on Fire Safety Science, place in Ljubljana, and it will take place from the 3rd to 5th September. And we're organizing that event in Europe. It's a prestigious conference in Europe very competitive, but we're organizing it, and I'm sure we'll do a good job organizing this event. If you have any work you want to submit, please, the deadline for the submission for papers will be around March, beginning of March. Okay? You can also submit posters, but it's a good opportunity to meet European community and talk to them and read articles across the globe. Now, right now, because as I said before, we have quite a lot of funding, and right now we have opened recently 2 positions. One for postdoctoral researcher. You can actually scan the QR code, and for senior researcher, like my level. We have officially 2 positions right now. We're looking for people because it's not easy to find good people actually that match the team and so on. So within USTC, if someone is interested in moving abroad and working in a really challenging and a nice environment where we work nicely, we collaborate a lot, we engage with people, we support people too, please let us know. To me, Jomas on LinkedIn, and then we can give you some more details about the position, what it entails. And as I said before, Slovenia is a beautiful country. It's very peaceful. It's very quiet actually sometimes, but so there's something for you to think about. If you don't want to do, you can also collaborate. You can also visit us. You can do an internship with us. You can work, come over on a research exchange. There are many possibilities. We're very flexible. I'm always willing to host people. Now, any questions? No? Yes, please tell me. So topics are similar to the IFSS. They're very similar to the IFSS topics. Like you have flame spread, you have fire dynamics, you have new energy systems or new novel fire challenging systems, PVs, lithium-ion. You have structural numerical modeling. So there are similar topics to the IFSS kind of symposium. Okay. So cool. Okay, so you cover all the topics more or less. It's like very general. Good. No more questions. Okay. Good. Let's see how long we're good timing. So let me drink a little bit of water because I'm a bit dry. Right. So that was a lot of information. So again, we talked about my background, and as I said before, it's good to go places and experience places and learn from people. Then we talked about FRISSBE project, my institute, ZAG. And then the last part is very specific about the challenges on fire safety of lithium in the built environment. And this is more or less how I envision the problem, how the problem is actually, I mean, it's a complex problem. For you, for the ones that are working on this, it's very challenging problem, but I think it's possible to tackle the problem in a way that it becomes simpler. And that's basically the main message I want to give about this specific topic. Okay, so one thing I was telling Professor Shayu before is that this topic itself, I'm developing it on my own because I'm the only one working on this. Sometimes I get help from students and so on, but that's why I'm here today explaining how I see the problem, and maybe we can collaborate with USTC or with other groups, and maybe we can find ways to actually the topic. But okay, that's it then. So this is how I divide the topic itself, so it makes sense. To me, first we're going to talk about the increased use of lithium-ion technology, and China is leading country in the world for that. We're going to have a look at the fire the statistical data, the fire incidents. It's not so easy. You will see why. Then we'll move on to the fire behavior itself. What's going on with lithium-ion fires? Then we'll look at how we can characterize one itself. And the last part is on safety design and standardization. And you will see this is also challenging because also at that level, there's also a lack of standards and norms to tell us how to deal with the situation. Okay? The five small parts in this subtopic that I'm talking today. So let's get started. As you know, we have increased use itself of technology, and I mean, China is, you are the leaders. Actually, you are the first one who really invested a lot of money. That's why you're so successful and great. And I've seen in Shanghai and here that many cars are just electric cars, electric motorbikes, and so on. In Europe, we're actually behind, but we're the second in the world. So one thing about, if you know, I mean, but this is a lithium-ion. This is a schematic of a lithium-ion battery. You have the anode, the cathode, the current collector, and so on. You have the electrolyte in the middle, right? And you have the lithium ions going back and forth. This is basic drawing chemist. For us, it's important to understand how it works. It's not that we will design this, but at least let's understand what's going on. Okay, this is the basic part. We'll get back to it later, and I will say why. So then because I collaborate with a research institute in Slovenia, and they develop the electrochemistry of these kind of batteries. They develop new chemistries. They change the anode. They always looking for lithium ion. Now they're looking at sodium ion. They're looking at metal, lithium ion metal technology itself. So one thing they want to do, and it's very clear, that they want to have high energy density. In other words, they want to have a smaller battery with a lighter weight with higher energy. That's unusual. The historic actually energy density since the 90s up to now, energy density in megajoules per liter or specific energy in megajoules per kilogram. Like since the 90s, lithium-ion batteries are going up actually in energy density, and they keep trying. Their goal, the whole aim is to keep going up. So that's the aim. Whereas for us, for fire engineers, we are stuck behind, trying to chase what they're doing. And I would say that it's very important to collaborate with those who are on designing the chemistries of this lithium ion or new technologies that come along. For instance, to give you an example, sodium ion batteries are also becoming popular. Actually, it's a push for it because technically they're safer, but sodium reacts with sodium reacts with air and will react with water. So you have sodium ion fire, you cannot remove or you cannot tackle it technically with water because it will react with water. So there's another challenge to it. So now, and then that next is that increasing applicability, of course, and then you see that this is China. It's the country in the world that has the most EV deployment in the world, and you have Europe and US is lagging behind and so on. But not just for electric vehicles, you have micromobility devices such as scooters, motorbikes, and so on. And it's the trends all across the place. In Europe itself, the only countries that have the most electric vehicles are Norway, Sweden, but slowly in other countries taking the same steps that we're replacing combustion engine cars with electric cars. So that's the future. This is going to happen. China, you can see already in China, but it's going to happen also in Europe. Let's see what the fire tells us, the fire data sets. So this is actually a plot that I made myself, that is the number of fire incidents per millions. I think this one, a number for incidents, and then over time. And then I just collected a few data sets, and I can tell you, for instance, the yellow one is from Hazard Dynamics, it's from Texas. This data set is not so reliable because it mixes EV cars plus and other things. So I cannot rely on that data. So for me, it's difficult to say this data is representative or tells me something. But I'm just putting there know that it's not easy to find data on fire incidents, and also it's difficult to rely on this data. Then you have this company in Australia, which is supported by the Australian government, EV Fire Safe, and they collect data from India on EV fires, on electric bike fires. They're a bit more reliable because they check the source. But then to me, and then you have the one from Netherlands, the red one, and that the Netherlands, that data is the best because when they collect data in Netherlands, they actually double check that the fire incident they collect is reliable, and they collect which kind of car was on fire, when it was happened, and so on. So far, these are one of the few data sets that are reliable. So based on this data set, I could actually extrapolate the likelihood. So I could divide of fire incidents per year for the number of vehicles, electric vehicles in that country. So I can give you I could potentially extrapolate a number that tells you what is the likelihood of EV fires. But I cannot do it with every country because every has different ways of collecting data. So it's difficult right now. It's difficult to say how likely a fire is going to be. Sometimes, so it's difficult for us as fire engineers to tell the EV industry, look, have X number of fires per year per vehicle to do something. So in first, we need to focus a lot on trying to get proper data, reliable one, so we know the likelihood. So then we can get the actual consequences. So we can say EV fires might not be so likely, or might be likely to be more dire, or be worse than combustion engine. So that's the first challenge I see on the data. That's why I'm working with the University of Liverpool with Dr. Martina Manes on trying to analyze all the possible data sets, including from China, so we can determine whether the data is reliable and whether we can compare the data against each other. So that's the first challenge. One other challenge, for instance, this is for EV Fire, the Australian company. And for instance, 90% of the EV fires result in an actual jet-like flames in fires. But 10% result in explosions. And that's something for fire engineers that don't actually look at that problem itself. When you design a car, design for this kind of event. You design for these, like 2-3 cars on fire, that's it. When you design a car park, you don't think about an explosion problem. So that's another challenge we have. That we're having also, we only don't have a fire problem, an explosion problem. Okay? So another challenge. Second one. So let's have a look at the fire behavior. And this here I go step by step too. So again, I showed before the basic of this ion diagram, but here I point something and I put here the chemical formula of each component. The electrolyte is a solvent and is very flammable to begin with. Then you have a lot of oxygen everywhere in the lithium-ion battery. Therefore, when you want to smother or kill the fire with lithium-ion, it's so difficult to do it because if you have a candle flame and you remove the oxygen from the candle flame, it will extinguish. However, in this case, the battery fire will produce its own oxygen. So it's no longer a hydrocarbon fire. It produces its own oxygen. So that's one of the challenges, I think. Another challenge we have with lithium-ion batteries. Then the first problem is thermal degradation or thermal runaway. So that's the actual first problem you have with a lithium-ion battery or with a battery cell. You need to know this thermal stability hazard. So you have to quantify basically the onset, when the whole process starts. That's why thermal runaway itself is a consequence of something that's happening before. So you want to know where the onset is. Is it at 80 degrees? Is it at 85? Because you want to know at which point the onset happens, right? So if you know at which point the onset, take measures to prevent that from happening. That's the first step. Then once thermal runaway happens, you have venting. If you have early ignition, then you have this, a jet-like flame, jet flame. In fire engineering for buildings, you don't deal with this problem. Actually, this is a problem that you don't deal with. Sorry. This is a problem that industrial safety people deal with, because when you have, for instance, a petroleum processing plant, storage of petroleum or storage of compressed gases, you deal with this problem. So there's another challenge you add to the whole problem. So then you have to quantify how big the jet flames are, how much is the heat transfer, how much you have to quantify the and so on, and the ejecta, because many particles are ejected, right? Then once one cell goes thermal away, if you have a battery pack, then you have propagation in all directions, right? That's why EV industry is very important that once one happens, one thermal away, once it happens, they have to avoid the heat generated from this cell going in all directions, affecting the next cells. Then the other thing is that you get, this is one experiment within the lab, the large scale experiment, and you get several type of gases that are flammable, but also they actually are harmful, especially hydrogen fluoride. If you inhale hydrogen fluoride, you can get lung damage. Okay, so then the next thing we have to do is like quantify how much toxic fumes and which are coming out from this problem. So it's another challenge. So then if we divide the problem into different steps, then you have this. You have first thermal runaway. Okay, then next problem is venting and ejecta. Ignition, you will have jet flames or flaming. If you have delay ignition, then you have deflagration. So we need to look at the problem step by step. Okay, that's how we, I think, can deal with the problem, because it's a complex problem. To tackle each step by the way, but each step at a time. So you want to avoid the thermal runaway at all costs. We need to focus a lot here. So here it's very important for the ones that manufacture the cells and assemble the cells, EVs, that to know to avoid this problem. If they avoid this problem, then they avoid a lot of work for us, for the fire engineers, fire researchers. Then if this problem happens, the next point is to avoid all of this flaming, but most importantly, because deflagration it's very problematic. Deflagration, you have a pressure wave that can have really bad consequences. So you see, then next question is, okay, if we know all these problems, is like lithium-ion fire is composed of different sub-problems. Okay, how do we characterize them? And that's what I said, we need to quantify each step, problem step. So then thermal runaway, we actually thermal stability, meaning that you need to know when is the onset, when happens, so at which point thermal runaway starts, what is the delay time, once this onset happens, what is the delay time, what is the voltage required, what is impedance measurements, what is the heat capacity of the cell, properties of the cell. If you want to know the energy release, we can actually look at the energy release of each step of the thermal runaway, of the venting and ejecta, of the flaming of deflagration, and we should look at each step. For instance, for manufacturers of vehicles, for them it's very relevant to know the energy release during thermal runaway, so they can actually put a cooling system that avoids this problem. Then if you want to have in the built environment, in the buildings, you need to know all these energies, you need to measure all of it. Then you need to characterize the gas species, so you know which explosion flow you will have, or which limit, the lower flammability bound or upper flammability bound, you will have the problem for specific gases, the particulate matter, the molar of emission, so you know how much is emitted and at which point, so you avoid explosion. Okay, I can tell you one thing, like Tesla. You know that Tesla has this division of they actually sell storage systems, and they know about this problem. So when they detect that it's thermal runaway, they actually ignite on purpose the fumes coming out, because they prefer to have a flaming problem rather than a deflagration problem, because they prefer consequences than the flaming problem. So they control a bit the problem itself. Then these are some of the methods that you can read in literature. And for instance, this is an ARC. This is accelerator calorimeter and USTC. And with this machine, you can actually look at the onset to thermal runaway. You have other specific. This is a method being proposed in the US, which is called fractional thermal runaway, and this measures the venting and ejecta energy. Okay, so that calorimeter you can combine with the oxygen calorimeter to measure the heat release or the whole process. But you need to, if you use oxygen calorimetry, you have to correct the chemistry happening, because again, oxygen calorimetry works in the principle that it measures the oxygen depletion. And as I said before, we have something else. We can use a bomb calorimeter to quantify the whole energy of a cell, or a large scale kind of sensible enthalpy rise calorimetry. So it's possible to measure the energy calorimetry, or the energy release of this problem. Then if we go back to the picture itself of quantification, if we want to look at thermal runaway, what do? We go to the ARC. If we want to look at the energy release, we can actually do the thermal runaway process. We can actually measure the energy release with an arc, or we can measure the flame propagation with ocean calorimetry or swag calorimetry. We can measure thermal runaway plus venting and ejecta with a fraction of thermal runaway, or we can measure the global one with bomb calorimeter for small cells, or for applications, e-bikes, e-car with visible effect. And toxicity, or the gases, basically, we can measure with FTIR or GCMS. So, but I mean, there are actually methods and tools to measure, to quantify the problem. We just need to measure them properly. So it's possible. And this is one of the few slides I have on safety design and standardization. And then, so we saw before everything about fundamentals, what is the problem per se. So what do we have in terms of standard design? Do we have any norms or standards itself? Then something I look, because if you look at the chain, is because it's a multi-stakeholder problem. You have the raw materials, somebody designs the cell, somebody manufactures the cell, they assemble it in the battery pack, they do a big battery pack at application level, right? You have an electric car, electric bike, battery energy storage system, and then all of these actually is brought to the built environment, basement to the houses and so on. So what I'm finding now, a lot of safety design at various levels, from early stage to application level, and there are standards actually in the world. You have UN standards, UL, IEC standards that actually somehow they tackle part of the problem. Then when you go any guideline that tells you how to design your building against this threat, we're still lagging behind. And this, I'm telling you about Europe. About China, I have no idea. I don't know. I have to discuss with Professor Xiaoyu. But you see, and these standard rules is because on the science we're still behind. That's why we have this, and that's what you will see in Europe, that many countries are banning the. For instance, in many places you cannot park your in the ground, or you cannot bring your electric bike in public transport because they're afraid. They don't know how to deal with the problem because of the lack of knowledge. Therefore, you have non-existent standard testing for that. So that is the last thing. Yes, and then basically, then final remarks about this last part is like, it's a multi-scale and multidisciplinary problem. That's why I think it's very important to work a lot with those electrochemists that are actually designing new chemistry, because otherwise, with electrochemists, will always chase the problem, because they will come up with new solutions, with new high energy density batteries or sodium ion or whatever, and those bring other problems, not just the ones I was mentioning before. Then it's always with them and to engage with them. Second point, the reliability of the data is actually questionable at the moment. So it's difficult to know, it's difficult to assess how big the problem is. Okay, and that's because we don't have reliable actually provide. Because if you want to do risk assessment, you need to know the likelihood of the event and the consequences, and you can't do that at the moment. Then quantifying the fire behavior and energy release, and quantifying the whole behavior is also very important. There are tools, and we can do it. Doing utilizing the right tool for what you really want to do or want to measure. Actually, you can also identify, if you actually quantify properly this behavior, you can actually identify some critical properties: onset to thermal runaway, flame length or jet flame momentum, and you can actually characterize the problem. Then you use that information for each cell. You can actually classify the lithium-ion cells according to their behavior, and that will help a lot in whether a specific cell design will be flammable or will be very dangerous or not. Okay, that's something we do already in fire science. We do that already. So I don't think why we shouldn't do the same with lithium-ion. And then the next thing is like safety design. And early stage design cells, they have some standards and some ways to do, although it's not the best. But then at the environmental level, meaning at the built environment, that's for us very difficult. Like transport is one of the fields that they have to do more work on. But in build, And I think that is the last slide. Yes, that is all, I think. And then you have any questions you want to discuss, please let me know. Any questions?
Yeah, thank you very much for very interesting presentation and an introduction of the challenges for the battery fire safety. So, any question from the audience here? Please.
Tell me.
Have you conducted? Because in your presentation, I see that the wetting and injection maybe happen before the.
You mean because we did some experiments? We have done large scale experiments from away, and now I'm trying to do this one. They are determining the onset actually.
Yeah, and
So, yeah,
in the battery, the wetting and maybe happen before the thermal runaway, I think.
which one?
The wetting.
Venting? No,
Yeah.
I mean, to me, venting is a consequence thermal aware, no?
Yeah, because the batteries, they will firstly happen the safety wetting, and then it will enter into the thermal runaway.
Yeah.
Yeah.
Because what I've seen is that you have the onset. I don't have here the slide for that, but you first have the onset, which happens at depending with 105 degrees onset. Then it starts to react, and then in the process of reacting, it creates overpressure. If you have a metal cell, that overpressure will break up, and you have venting.
Yes.
Right?
Yes.
That's how I see it. I mean, that's how I see it. That is first. That venting is a consequence thermal away, and it's in the process actually. You can also say thermal away is the whole process, and within thermal away you have venting and ejecta. To me, it's important to do it step by step, so it's easier to actually quantify the problem.
Yes.
Yeah.
Yeah. Thank you.
No worries. Yeah, but I mean, it's a valid question. I think it's very relevant, and it depends how you see it. But because I think step, you can it becomes easier to tackle the problem.
Yes.
Okay.
Yeah, I have you mentioned the ignition about early ignition and delayed ignition. Yes.
Yeah.
I wonder how to distinguish the early ignition and delayed.
So
What's the standard to
what's
evaluate?
so this is something I just mentioned briefly, just because also I don't know what exactly should be the because for instance, if you want to look at thermal degradation or thermal runaway, the moment is when the onset. Onset means the beginning of the process. So when you have the onset, this happens 110 degrees, and then you have the big jump between the onset and the peak thermal runaway. It takes some time. That is time to ignition, or ignition delay time, or delay time to thermal runaway. But it's not the same concept. I mean, I just put it there as an idea, not necessarily that because it's standard. Because also something I don't know if it makes sense to call it that. You know, I think at some point people who work on batteries, hopefully you too, we have to sit down and discuss what is the best, what is the concept that we say that makes the most sense to characterize thermal runaway. Is it just onset? Can we measure the voltage, or can we measure the ignition delay time or time to from the onset to the peak temperature measured in the arc? So it's something I don't know yet if it's the best, but it's a very good question actually. Yeah, good question.
Thank you.
Hi, I'd like to ask you a question. What test techniques can be used to monitor the type of smoke during runaway?
The smoke, you mean?
Yeah.
What I know, when you do smoke itself, let me go here. That, for example, when they do smoke, they measure because I think they can measure. I'm not sure if HF or CO2. There are certain gases. you look at the gases here, let me go back to the, let me see here. You can actually install some detection devices that capture some of these. They can capture the carbon monoxide. That's the easiest one because that's when we use construction engineering or engineering itself. There are some that will capture the hydrogen fluoride or the methane. Look, see, there are some of these ethylene too, actually. So then you will probably install. You have a battery energy storage system, a big one for industrial. You will then install one specific detection system that will target one of these gases. So you know that is detecting thermal waste happening, you have venting happening. So then you will know that this is happening, so you have to do something. Tesla, as I said before, they detect some of these gases. The moment they detect the gases, they ignite the gases because they know that having a fire problem is better than dealing with an explosion problem. But yeah, that's also a possibility. And many people are measuring also. You have here, let me see, let me go back to the slide. So they're also measuring actually the battery management storage, the system itself. This, each battery pack has, actually they will measure a terminal voltage. If a cell or a group of cells starts to deviate, then we shut down the system. That means it's a problem. Or they will measure the temperature itself. Or there are many ways that I've seen to kind of detect the problem. But to me, the goal is you have to detect as early as possible. When you detect gases, it's too late. Already from what happening, you should detect the onset somehow, and that's to me the challenge. Detect. Okay. Yeah, very good question. Thank you.
Professor, your speech is so wonderful. So I want to ask your question. Electric arcs occur during the battery storage. Is it a point worth of research whether the electric arc induced the thermal runaway of bacteria?
So that's a very good point. Again, Professor, your students are very smart. So this is a very good point. So this is how me, with my expertise in fire, how we did the problem. But then in this whole presentation I gave, I'm lacking the electrical part because there's not my background. And this is a good point. That's also, you have this arc problem, you have this overcharging problem that I will have to call someone who's expert on electricity or electrical engineer to tell me what it means. I do the test in the arc and it measures the voltage, but to me, I don't know what it means itself. But that's a question actually that we should involve the electrical engineers into the problem. Because we are not experts in electrical engineering. Them involved to tell us what it means with electrical voltage, what it means when you have overcharging. Because I know that certain fires that happen because of when we're doing charging, and that's a good question. Again, as I said, the last slide is a multi-stakeholder. We have to involve it cannot just be us trying to solve the problem. We have to deal with electrical engineers, the electrochemists that are designing the chemistries. Otherwise, if we only work on a problem, we'll always chase the problem because they are coming up with new solutions all the time. And I think to me, it's a waste of resources that we always have to chase. We either have to tackle the problem from the early design. So that's more is how I see it. I hope I answered your question, but thank you. That's a very good question, actually.
Okay. Hello, Professor. Nowadays, the lithium-ion are currently very popular worldwide. But with the depletion of lithium resources, we are also exploring other new types of batteries like sodium batteries and batteries. So, Professor, do you think this path is feasible, and in which areas should we focus our efforts?
So, that's a very good point that actually resonates with me. As I said before, these people who work on it, and many everywhere, because of media, they're saying lithium-ion might not be the safest. That's why I see companies that actually work with certain research institutions that are starting to develop new types of batteries, chemistries, not just lithium, lithium metal, sodium, lithium copper, solid state. So some of them bring new challenges. As is reacting with oxygen, reacting with water. So there's a new problem that brings, if you want to use sodium-ion batteries for other applications, then it's a new problem we'll have to face. Again, if we want to really be smart, we shouldn't just change, because if the guy who is doing the electrochemistry is designing something new, I'm the one at the end that is trying to fix his problem, because he's creating a problem. The moment he designs a new chemistry, a new battery, he's creating a new problem. So we are the ones that trying to solve what he's creating. So to me, the point is that we collaborate with that person who's creating the electrochemistry or the new chemistry of the over using new sodium. So he understands that he should really focus the design, not just really on the energy of his battery, also on the safety part. And I'm trying to do it in Slovenia with the national chemistry lab, where they create this sodium ion and new battery chemistries, and I'm telling them, you need to work on focus. Otherwise, it's going to be impossible for us to tackle all these problems. But this is a very good question, and to me, the only way to solve it is work with these people as early as possible. Yeah.
Okay, thank you.
Hello, Professor. My question is a bit different. At present, the artificial intelligence industry is developing rapidly. How do you view the application of artificial intelligence in fire research? Or how do you think our research can be combined with new technologies such as artificial intelligence?
Yeah. That's a question that is outside my comfort zone. So it's the only thing I can say is that I think artificial intelligence itself, it helps in many industries to become more efficient. And I think the same should happen to fire safety engineering, that it should be able, for instance, I know that some companies are developing some tools that cameras, video surveillance cameras, should be able to detect early possible a fire. So that's another application of artificial intelligence to detect as soon as possible. So then I think it's possible that artificial intelligence should permeate into fire safety engineering. And then, so basically your detection time becomes from being 2-3 minutes, being a few seconds. So you have more to evacuate the building. So that's a good thing about artificial intelligence, I think, a good application. Then, and then I'm gonna be very controversial in this case. Using artificial intelligence to predict physical phenomena, I think that's a bit challenging, because physical phenomena fundamental understanding the mathematics and the physics and the chemistry, and I'm not sure at which point, or I don't think now currently artificial intelligence is ready for it yet. Maybe in the future, who knows? But that's what I think is good for detection, perhaps. On the other hand, I don't think it can predict fundamental phenomena. Yeah, I think that's my controversial say about it. Yeah.
Okay, thank you very much for your kind answer. And AI is a promising technique now for the fire safety research. So that's why the audience are so interested in this kind of question. So we also have a lot of audience online, and more than 10 questions.
Oh God.
But I due to the time reason, I can only pick up some.
Okay.
Ask you. So the first one is what are the main goals of the FRISSBE project in terms of fire safety?
So let me go back to the FRISSBE thing. So I didn't put it here, but I mean, one of the goals is that we create, let me go back to the FRISSBE itself. No, sorry, this is, here it is. So the main goal of this FRISSBE project is to establish a new research group in the field of fire science, and then so we can actually bring high or cutting edge knowledge into the fire safety. And actually, I think we are succeeding because, again, one of the things I'm saying that we are good at, we brought funding, because that's one of the objectives of this funding, is that it hired us, but also it meant that we had to find more, so we became sustainable ourselves as a unit. And then, and as I tell you, I'm working on fundamental work of flame spread microgravity environments, and that is cutting edge, I think, or it's kind of edging the knowledge and trying to expand the knowledge, and that's something that to me is worldwide unique, because there are not many people in the world that work on this topic. I think all the topics, not just this one. And recently, Professor Grunde Yomas and together with Nick Cruz, our PhD student, they released fire safety guideline installations that have had really good success. Many people have come to us because of that guideline. So then maybe that guideline will be transposed into standard, which means that our research has a huge impact on society, and that was one of the goals of the project, having a big impact on science and on society.
Okay, thank you. So another question is, how does the FRISSBE project incorporate the participation patient into its methods for improving fire safety?
So that's a good thing about that's, and I have to mention Professor Grunde Yomas, that he's very good at engaging with the industry. That's why, I mean, I cannot mention which companies, but he brings fun from industry, and he actually all the time discuss with industry, different companies in the region, and we get projects from companies all across Europe, actually, even from all the way around to the US, to America. So that actually engage a lot with industry, and it's good for us because we do the basic fundamental research, but at the same time we also do the applied research, because for an industrial partner they want to find a rapid solution for a problem they have, and actually offer that to them. They can actually find a solution for the problem. But that's I have to say, it's thanks to Professor Grunde Yomas. He's very good at that. I have to learn from him, actually, from my boss. Yeah.
Okay, thank you. So another question is, how to implement effective isolation measures to multi-story building design to reduce the spread risk of lithium battery fire?
In building, a good question. Yeah, I mean, they're making really good questions, actually. I actually, first, I think we should understand how the problem behaves. So that's what I was explaining before, like regulation, we need to know how much energy is released. So then if we know that, we can actually design a building in such a way that, for instance, if one battery pack releases 1 kilowatt, like 1 megawatt of energy, imagine that somebody comes to your home and wants to sell you an energy storage system, and that has, I don't know, X amount of energy. If, because of the fire, this battery energy storage system will release 3, 4, 5 megawatts within 5 minutes, 1 minute, that is something you cannot design for. That then, at that point, you take the decision that either you isolate this kind of battery energy storage, or you install it outdoors, outside your building, so you avoid a problem. That's one specific, for instance, example. Other one is for battery for electric vehicles, micro-mobility devices. That if we know how much energy they release, then we can actually design buildings, transport, like in trains, and then we can design those to actually counteract that kind of energy release or the smoke. For instance, or you have batteries into e-scooters or e-bikes, and you take them you store them in that one place. That place has to have plenty of ventilation, because you know the smoke is going to affect people if there's a fire. Put in place, install powerful ventilation system to remove all the exhaust gases. So that's some example, but again, we need to go back to the fundamentals, understand what's going on, quantify it properly, then we can put in place measures to problem.
Okay, thank you. The last question, finally. Okay. How to promote the unification and improvement of global lithium battery fire safety standards through international and knowledge sharing?
So that's something I actually not sure how to do either, because that's very political work then. So then at that point, you are going to the political side of life, because one thing is that you do research, you get the funding, you promote that, and then at some point you have to start being very loud. That's why, for instance, on LinkedIn, FRISSBE is very active, and Professor Gunde is very active, because getting a very short, a precise message across society, across the community, and then eventually, by giving these messages, authorities, the ones who decide to do the standards, the guidelines, we decide to make a guideline, a standard. That's a very political work, actually. That's something a bit, I don't know how exactly to do that at the moment, but I know that Professor Grunde and Professor Jose Torero, they're very good at it. They have been years, but that becomes political.
Yeah,
So
definitely.
it's a challenging problem. Yeah, I know it's a challenging part of the problem, but yeah.
Yeah, definitely. We can work together on these kind of global challenges to make our energy storage more safer and
yeah, I guess collaboration is the key. Collaboration between us, collaboration with the industry that creates the batteries, collaboration with the electrical engineers. That to me is the best way.
Okay, thank you very much for your presentation, and everyone online and on site for your kind attention to the lecture. Okay, thank you everyone.
Yeah. Any questions? Just drop me a message or an email.
If you have questions, please email Dr. Ulises.
Sure.